talk about properties of these estimators or quantities related to the estimators. And what we proved was that we actually calculated the covariance of beta hat and E, and it turned out to be this covariance matrix. This contains a lot of information. So this part, for example, contains the marginal covariance of beta hat, covariance matrix of beta hat. This is the marginal covariance matrix of E. And this cross covariance is 0. So, and you're under the normality assumption. So under the normality assumption, we had that, in fact, under E2, we had that beta hat E is distributed like normal. If you recall, the mean is beta 0. The covariance is sigma squared x transpose x inverse is 0, 0, sigma squared I minus h. So we have the full distribution, which is multivariate normal. And then this 0 here had a significance. Anyone remembers what the significance of this was? Yes.
They're independent.
They're independent because
They're uncorrelated, and they're normal, which means they're
great. Yes, they're uncorrelated. The 0 means uncorrelated, but because they're also multivariate normal under that E2 assumption, they would be independent. So this means that beta hat is independent of E. What was the other conclusion that we got from this, which was really important? Great. So from this, we get that beta hat is independent of S squared, which turns out to be this. N minus, I'm going to write D. D would be P plus 1 for simplicity. Okay. Because S squared is a function of E, beta hat is independent of S squared. So independence is that strong conclusion. Okay. Then what do we do next? So no one remembers what we did towards the end. So what is this useful for? Yes.
estimating the distribution of S squared.
Estimating the distribution of S squared. It's not useful for that actually. So separately, we know that n minus d, let's say s squared divided by sigma squared, this would be e over sigma squared. So I sort of just told you what this is, right? So we know what e over sigma is. So e over sigma has a Gaussian distribution, multivariate normal distribution with covariance I minus h. So dividing by sigma, remove the set at sigma squared. So it's a multivariate normal, but the norm would be like chi squared with n minus d degrees of freedom. So that's something that we mentioned, but we haven't proved. Later we'll prove it at some point. So we have this. So now what is this useful for? I know that. I also know that beta hat is normal with mean beta variance sigma squared x transpose x inverse. Why do we go through so much trouble figuring that out? Last 15 minutes of the last lecture. Basically. I'll copy these to a new sets of slides while you guys think. Inference. Okay. So that's sort of related to this set of ideas. So you want to do uncertainty quantification, you want to do hypothesis testing, confidence intervals, etc. So what's that useful for? I'll do it here. Add a page. So what is this useful for? to do hypothesis testing to get confidence intervals. That's useful for that. Okay. So for example, so hypothesis testing, that's something we started to do. Have y, let's say I equal beta 0 plus beta 1 xi1 and up to beta p xip plus epsilon I from 1 to n, and say I want to test whether beta 1 is 0. So null hypothesis is beta 1 is equal to 0. Alternative is beta 1 not equal to 0. Right. So if beta 1 is equal to 0, it means that for like this feature, each one of them is a feature or covariate that doesn't affect y. So this is something that people really are interested in. What features or what covariates affect the response or not. So just to recall, so suppose we solve the OLS, we get beta hat equal 0.001, 10,000, 20. So I'm going to conclude that beta 0 is 0, beta 2 is like beta 0 is beta hat 0 is this. I'm going to assume this is small, so beta 0 is small, 0. Beta hat 1 is large, so I'm going to say beta 1 is non-zero. This is sort of quite large, so this is non-zero. So I don't need to do hypothesis testing. Stat departments are useless. Okay. Why would I need to do hypothesis? I can just look at this, see like 10,000 is large, 0.001 is small, so beta 0 is 0, hopefully. This is large. This I can remain large, 20 is large, you know. You already see like you get, yeah.
You can't really do everything. It depends on the variance. So like it could have a very large variance so that 10,000 might not actually be that large.
Okay, good, great. But I want to post it a little bit again. So these are the numbers that I have seen, right? What does it mean for it to not be as large? So the variance is some sort of an abstract idea. I have a set of data, I just do the regression, I get these numbers. These are the only numbers that I'm going to see. So what do you mean by the variance being large, the noise variance being large? So can you like elaborate a little bit?
If you like repeat the experiment multiple times, like you get different values with beta 0 that are more spread out.
Great. Okay, so that's the idea. So we now at this point switch to the abstract view. So abstract view. Beta hat is like normal between beta and sigma squared x transpose x inverse. So this is now beta is a random variable. I'm not going to see this. This lives in abstract mathematical space. If I repeat the experiment many times, suppose beta is completely 0. Okay, even if beta is completely 0, like 0, 0, 0, because of this variance here, and because of this term, the values that I'm going to observe are not going to be 0. They're going to be fluctuating around. And if the sigma squared is like a million, or like 10 billion, then this is very likely to see. I'm going to do it. I might see something like that. I might see like something close to 0, but I'm going to see very large values regularly. And so I don't know that this is because of this variance, like because of the noise actually, or because this was actually 0. Okay, unless I have some sort of an idea of the noise, so that's where the statistics comes in. So statistics doesn't care about this particular example, it cares about like at least frequent statistic cares about. If you repeat the experiment, maybe you don't see 10,000, maybe next time you see 1, maybe next time you see -5, maybe next time you see 1,000,000. Who knows? Okay, so it depends very much on this. So if you generate something which is, so if the sigma is very large, the beta hats that you get, so this comes from the noise variance. This is like the normal 0 sigma squared. And so that sigma squared sort of propagates to all the estimators. You can see exactly the covariance and the variance of, let's say the variance of beta hat 1, in our case would be sigma squared x transpose x inverse 2, 2. This is like the second element. So this would be a matrix. The first element would be, on the diagonal would be the variance of beta hat 0. The second would be, this is the element that I'm looking at, which I'm saying 2, because I'm going to index this with 1, 1, 2, 3. So 1, 1 would be the variance of beta hat 0. So this quantity could be large, and so beta hat could have like a large variance. So that's where statisticians come in and then try to estimate this variance, and then compare the value that we observe to this variance. And you know, for example, a normal variable can like usually like with 95% or 97%, 95% of the time it's within 2 standard deviations of its mean. So if this standard deviation turns out to be like really small, that's this whole variance. Standard deviation would be root variance of beta hat 1. So that would be sigma x transpose x inverse 2, 2 root. So this turns out to be very small compared to the actual value that we got, which is beta hat 1. So if beta hat 1 is like, if beta hat 1 divided by the standard deviation of beta hat 1, if this is large, then most likely beta 1 is non-zero. So I can like be more confident. I'd be confident that beta 1 is non-zero, because the noise can like produce, if like the sigma is, let's say this is 1, the sigma is 1, like 95% of the time I'm going to see something which is in -2 and 2. It's very unlikely that if this was 0, I would see 10,000. So 10,000 could come from this, it should come from this one. But if this turned out to be like maybe 50,000, then that's very reasonable within the range of the randomness. So I'm not going to guess that beta 1 is non-zero. So if this is 50,000, this is all within like 2 standard deviations, so could have come from the noise. Not the whole number, maybe like you'd get something like 24.0, like the whole number is very unlikely to see. Sounds good? So I keep repeating this so that you understand what we're doing. But we don't have the standard deviation. Why don't we have the standard deviation? From population, a little bit more precisely, like what don't I know about this? Can I calculate it? Like I know X. I can. Why not? Beta based on size?
Like the sample data, not like the true population.
That's true, but the idea is that based on the sample, I can. So the thing is, this beta hat 1 is fitted using our current sample. So it's going to be like the random variable, abstract random variable depends on the current sample, because I specifically trained it on Y and X. So it's like there is this Y1 up to Yn, right, which is like X beta 0 up to beta P plus the noise. I plugged in these two into the least squares and beta hat came out. So there's this relation. So there is the population, as you mentioned, version, which is a random variable. So this X you're going to assume to be fixed. Okay, so there's a population version. It depends on this population Y if you want. I'm going to call it abstract Y. And so that has that distribution. There's also like a realization which you actually can observe, so like that, those numbers. But the main point is that there is this parameter that I don't know. If I knew this, if I someone give me the population, let's say noise level, so the noise level and the sigma, then I would have the standard deviation. Right? There's a simple like answer why we don't have it because we don't know these things. Okay, but whatever we don't know, we can estimate. So the estimate is, what is the estimate? It's natural estimate. S squared. Yeah, so S squared is the natural estimate. So if you remember, the standard error is just the standard deviation hat. Just add a new page here. Yeah, I like the idea of population. So what I call abstract, you can call population. Same name. Well, not the same name, but the same idea. So let's try adding one more page here. The disk using beta hat, right? Which is X transpose X inverse, X transpose Y. So you can see it takes function. So a standard error of beta hat would be a standard deviation hat. So it's an estimate of the standard deviation of beta hat. And it's just obtained by replacing sigma with S. So now this is an estimate. And it happens to also be a random variable as well. So now because it depends on S is a random variable. There is the abstract version, there is the observed version. So in practice, you can observe a value of this. But if you repeat the experiment again, this thing is going to vary. Every time you do, you get a different standard error because you get a different S. Let's say X is fixed. But the actual standard deviation is something constant, like it's attached to the population, attached to the abstract random variable. Okay. So we have an estimate. Now I can form, now we can form beta hat 1 divided by standard error of beta hat 1. And if this is large, then I'm going to decide that beta hat 1 is non-zero. Okay. If large. Say that beta 1 is non-zero or something like that. Okay. So that's the idea. Sounds good. So what we want to do is determine how large. Okay. How large should it be? Still, I haven't solved the problem because I don't know when I should declare that this is large. Okay. So if I divide it by this, so anyone knows what so beta hat 1 divided by the standard deviation of beta hat 1. Anyone knows what the distribution of this guy would be? Beta hat 1, yeah. So that was a trick question. So this one, not this one. So if I divide beta hat 1 by the standard deviation of beta hat 1. No. Normal, yes. Standard, standard, yeah. So let's say under null, under the null distribution. So under null, H naught, we know that beta 1 is 0. Okay. Then beta hat 1 is like normal, which means beta 1. And variance, which is sigma. I'm going to write it as a standard deviation of beta hat 1. Right. This is a population quantity. This is non-random. This is this quantity. Okay. And under the null, this is going to be 0. Right. So if you have a normal variable divided by, so this is actually, sorry, this is going to be variance. Let's say standard deviation squared, which is the variance. So if I divide it by the standard deviation, whatever the variance is, I take the root divided by that, that would be normal means 0 and standard normal. Okay, that would have worked. Then I would know that, for example, how typical is for different values of standard normal to happen. Like in -2 and 2, there's like a 90% chance from right, or like something like that. Like 1.9. So -2 and 2 is actually higher probably. So if this was this, like the probability that beta hat 1 divided by standard deviation of beta hat 1 is in, let's say, minus 0.96, 1.96 is, this is going to be like roughly 0.95. Okay, because standard normal, like we probably 0.95 is something like that. I forgot 0.96 or like 2, rounded to 2. Sounds good? Right, so if I had the standard deviation, I could do this. And for example, if you want to be confident, confidence interval means, I'll get to that, but this gives me like, so if I reject, then I'm not in this interval. It gives me 95% confidence that I'm good, because with like under the null, this happens like 95% of the time. So 5% of the time that doesn't happen. And so if I reject, when I'm outside this, only 5% of the time under the null, I'm going to be wrong. So that's like false positive rate. And so that's what we do. So for example, you want to have a level for the test, they call it significance level, or that level for the size of the test. So if I reject, so you can create a test. So reject H naught if beta hat 1 divided by standard deviation of beta hat 1. Now, absolute value is if it's bigger than 1.96. So this would be our test. So if it's bigger than this, I'm going to reject. This test will have a size like of 5%. So under the null, so the probability, I'm going to say under the null. Condition under null, let's say. Or like, let's not do conditioning. I'm sometimes going to write like under the null. So under the null, the probability of rejection, so for this test, the probability that I reject H naught will be 5%. Because 95% is within this interval, 5% is outside. So it doesn't say outside. So the probability of rejection will be 0.05. And this is how you do hypothesis testing in frequent statistics. So you try to build a test such that under null you're wrong like small number of times. That small number is called alpha or significance level or size of the test. Significance. Or just level. So if you want to usually set a significance level. You want to test at level 0.05, which means that under the null, at most 5% of the time, you're wrong. If you repeat the experiment many times, and that gives you that, okay? Right. So it's very reasonable that, sorry, this is not correct. Is this correct? Probably correct. Yeah, this is correct. So for normal, that's like the 95%. So what this is saying is that if I have a normal distribution, right, if I want a symmetric interval, how far should I go such that this part is 95% of the mass, and this part is 5%. So it's like 0.025, 0.025. Yes.
If we're doing that, we can also reject if we're less than 81.96 as well, right?
Yes, so this is doing that. So absolute value bigger than 1.96 means that I'm either above 1.96 or below negative. Because this, if you think about this, this takes care of the sign. Anything outside this interval would have the absolute value here. So this 1.96 is, anyone knows what this location is called? Or this one, or? So like, statisticians, they call it something related to this distribution. The location where you see like alpha percent of the mass. Below it, like, yeah.
The alpha over 2.
So this would be the alpha over 2, I believe. So what is the name like? Sorry? Critical value for the test, yes, but like associated with distribution, there's a very nice name associated with it. Z is fine, but let's say I change the distance. So Z is usually because you're talking about the normal, a more general name. So I have a distribution. The probability that, let's say, I have a statistic T, the probability is less than T is, let's say, alpha. This location such that the probability that below it is alpha. What is it called? Sorry? Type 1 are these are associated tests. So this is about the distribution. P-value, no. P-value is again associated with tests. So, great. Okay, that's the name. So quantile. So the quantile is basically the inverse of the CDF. So this is the CDF, right? Ft of T is this guy. T would be like Ft minus 1 of alpha. If you set it equal to alpha, you invert this relation. So it's telling you for a given alpha where you should look such that alpha percent of the mass is below this. So the location below which you have alpha percent of the mass. So this is like alpha quantized. So you'd put like F minus 1 of the normal, let's say normal 0, 1. This would be actually this part would be like the alpha over 2th quantile of normal 0, 1. Like 0.25% quantile. Quantile is a very natural, like, statistical quantity. So if you know CDF, quantile function is just the inverse of the CDF. So CDF tells you, so you give the CDF T, the T tells you what is the probability that you're below T. Quantiles tell you I want the probability. I give you the probability, give me where I should stop, so that the probability of below this value is alpha. So these quantiles sort of come in. So the quantiles of the normal distribution comes in. And I'll talk about the p-value. So this quantile you call, you can also call it z-value because they're quantiles of the normal. So we'll talk about z-values a little bit. You can call something else z-value, which is a little bit better. Z-value is like p-value. I'd rather call something random z-value rather. This is better called quantile. Questions? So we're still in the trick question. So we followed up the trick question because the standard deviation, this is not useful. It's good, but someone has to give you the sigma. So if I tell you the sigma, then you could do the steps. Okay. So if some oracle, like someone with like knowledge of hidden things, give you the value of sigma, then you can calculate the standard deviation, you can compute this would be normal. So what we have to or what we ended up working with is this guy. So instead of dividing by the standard deviation, we divide by the standard error. So this one actually can calculate. So this would be a valid test statistic. This wouldn't be a valid test statistic because it depends on the unknown parameter. There's sigma in there. Okay, so good if you know the sigma. So in some cases, you may know the sigma. So you can use this test statistic if you have a null distribution. I sometimes put an H naught here. So under null would have a normal distribution, and you're going to be done. However, like in more practical settings, we don't know sigma, so we work with this. So can I say that this has a normal distribution? Does it have a normal distribution? Beta divided by standard error. Now, like the answer comes, that will be p distribution. Okay, so that's the thing that makes things a little bit complicated because the standard error depends on S, and S was calculated based on the residual, and the residual was calculated based on beta hat. So potentially, this guy and beta hat are related. Okay. Because again, so standard error is based on the residual, based on S. S is based on the residual is based on beta hat. So all these quantities are based on beta hat, and eventually they're based on Y and then on epsilon, the actual error. So they're related. When we have like relation, So if I have these two partially related, then I should divide, the distribution could be complicated. So I just wanted to make sure that you understand that. Here, this was a constant quantity, non-random. Here, both are random and potentially dependent. When you have dependence, you have to worry. The good news is that we went through all this trouble to show that beta hat and E are independent. So remember, E is y minus x beta hat, so it depends on beta hat. Like functionally depends on beta hat, but we showed that statistically it's independent, which is a very nice result. Anything that looks like this potentially could depend on beta hat statistically as well. Functionally, it certainly depends. But statistically, we showed that they're independent. So S is squared is independent of beta hat. S is independent of beta hat. So from this, we get that. Let's say beta hat 1 is independent of standard error of beta hat 1, because this is just S root X transpose X inverse, let's say 2, 2. Oh. Sorry. Okay. Stop this. It's back. Here's a delay. Okay. The inference is not really good. Oh, fine. So that would be independent. So now I'm in business because I know the joint distribution of beta hat 1 and a standard error. Yeah, so these are independent. Okay, and now I know the distribution. So how it does a t distribution, let me show you. And so beta hat 1, so under the null, H0 is beta 1 is equal to 0. Under the null, we have beta hat 1 is normal means 0. Variance sigma X transpose X. I'm going to do it with I. Okay, not I yet. Okay, let's do 1. 2, 2, you figure out the rest. So root, I'm going to call this, let's call this V2. Okay, so it has normal, which means 0, sigma V2. So I know that beta hat 1 divided by sigma V2 is normal, which means 0 and 1. I also know that, what else do I know? I know that E is normal between 0, sigma squared I minus H. So I know E over sigma is normal between 0 and I minus H. And I actually know that this we did. So N minus D times S squared divided by sigma squared. This is going to be just E over sigma squared. So this is going to be chi squared. N minus D degrees of freedom, D being P plus 1. So the standard error of beta hat 1 would be, this is going to be S V2, right? If this is V2, I'm just going to replace sigma with V2. Okay, so I have this is normal, and I want to go from that to beta hat 1 divided by the standard error of beta hat 1. So this is going to be beta hat 1 divided by S V2. And we write it as beta hat 1 divided by sigma V2, which I know times sigma divided by S. Okay, so just multiply and divide by sigma. Okay, So this has a normal distribution, we know, under the null. And this one is very close. So we know the distribution of this. So I'm going to rewrite this a little bit. So this is going to be equal to beta hat 1 divided by sigma v2. That's this part. So this comes here. The other one I'm going to put in the denominator. So it would be s divided by sigma. Okay. And furthermore, I'm going to do it a little bit more. So this step is clear, right? So if I do that, so first here things would cancel out. You see, like this cancels out. We get back to the original one. So this one, I'm gonna now just rewrite this as beta hat 1 sigma v2 divided by, I'm gonna write it as n minus d times s squared sigma squared. I'm gonna put a root here. And then root, and then divide by n minus d. Okay, it's just rewriting of that thing. So n minus d would cancel out, and the root would just give you, this would be sigma squared, would give you s over sigma. So this is exactly the same thing. I just, again, multiply and divide it by n minus d. Now, this thing is chi squared with d n minus d degrees of freedom, as we showed. This thing is normal, which means 0 and 1. And so what I'm doing is I'm dividing a normal random variable by the square root of the chi-squared random variable divided by its degrees of freedom, the minus d. And these two are independent. So the numerator and denominator are independent. So this is the definition of a t random variable. So if you divide a normal random variable by the square root of a chi-squared divided by its degrees of freedom, and the chi-squared and the normal are independent, this is the definition of a t random variable. Okay, so by definition, this would have a t and minus d degrees of freedom. So independence is important. Anyone knows why it's called t? Yes.
The person who made it, wasn't his last name start with T or something?
Great. The end of T. So the students T, yeah, right. So about like 100 years ago, like maybe even exactly 100 years ago. So what he did is like he calculated the actual PDF of something like this. So you have a normal divided by the square root, the chi-squared independent of it divided by n minus d. So you can calculate the PDF using the rules of change of variable. And you can tabulate it for different values, and that's what he did. And in his honor, it's like T. Not very informative of his name, but that's how much you get in statistics. You like maybe a tiny bit of your last name remains. So T and minus D. Okay. So at this point, this is how people in modern or define a t distribution. So you have a normal 0, 1, let's say divided by root chi-squared. I got, m divided by m. This is going to be tm if both variables are independent, or two variables. So the significance of this is that because we're dividing by something which is random, sometimes this gets very close to 0 by chance. And you divide by something which gets close to 0 by chance, this would blow up. So this t distribution in general would have a heavier tail than normal. Heavier tail means the extreme values are more likely. So if you have like a normal distribution, the tails go very fast, like e to the negative x squared. For t distribution, if this degrees of freedom is not large, you might like the tails would like, you can't provide it very well, but the tails are heavier. So you have higher probability of observing extreme values. When n goes to like 4, this is t. for m is small. When m is very large, or when the n minus d is very large, and sample size is very large, this is gonna approach gets close to the standard normal. So our standard normal approximation, because the square is going to be very good estimate of sigma squared, and so this extra factor would go away. But when things are small, pi squared, this could get close to 0 by chance, and it could go up by chance, so you get heavier tails. So this is like precise tails of it is controlled by the t distribution. Sounds good, right? And then once I have this is very close to what I had before. See, I can actually like tabulate it, or in modern world, you can actually compute it on a computer. So it's baked into R. So you give this the number of degrees of freedom, you know, the sample size minus here, D is the number of parameters, which is usually P plus 1 if you have intercept, or P if you don't have an intercept. And so you know this distribution. Now what I can do is I can test. So hypothesis testing for beta equal to 0. We do like beta 1. Beta hat 1 divided the standard error of beta hat 1. If this is bigger than, I'm gonna write it as t n minus d alpha over 2, let's say. It's like absolute value of it if you want. Then I would reject if so this is really think about it, it looks like the t would look like so it looks like a bell-shaped curve, but it's like heavier tailed. Symmetric around 0, the mean is 0. So what happens is, like, because it's symmetric, I'm going to take alpha over 2 here of mass. So sorry, the mass here would be alpha over 2. So this would be t n minus d of alpha over 2, which would be negative. So that's why I put an absolute value here. And then negative t n minus d alpha over 2, which is going to be positive, is going to be this part. And this is going to also have an alpha over 2. So the rest here would have 1 minus alpha, probably like mass. So usually you take alpha to be 0.05. This is like the standard. So this would be like 0.025, and this would be 0.05. So you can write it like that, or you can write this t n minus d of 1 minus alpha over 2. Because below this point is like 1 minus alpha over 2 of mass. So this would be a positive value. This would be a negative value, but the absolute values are the same. So in any case, you can figure out the location. It's very much like you decided based on the Gaussian, but now it's a different distribution. So this is like a so this is our beloved like t-test. Okay, or like statistician's beloved. Maybe not yours, but statistician's love. Okay. This is how you do a test of like significance. This is sometimes called significance of this particular coefficient. Okay, significance here is that level. So we reject. So significance is like an abstract concept. Significance means, what does significance mean? So let's say when I say I'm going to reject at significance level 0.05, what does it mean? So what is the point of doing this? Why I want to come calculate basically quantiles of t, say put a quantile of t here. So I reject when I'm bigger than certain quantile of t, what would be the statistical point of that? Why not reject for smaller values? So I can always reject, let's say, like if you want to be sure that you don't miss anything, you can just always reject. Beta divided by a standard error of beta hat. If it's bigger than 0, reject. If it's exactly 0, then maybe not. Yeah.
That increases the chance of errors.
Sorry?
It increases the chance of errors.
The chance of what type of error?
So the bigger you make alpha, the smaller your type 1 error gets, but then your type 2 error is compensates back.
The larger we make alpha,
The smaller the type
This-
1.
the smaller type 1 error. Is that correct? So the larger,
Yeah.
the other.
Large alpha is like-
Okay, so this alpha basically controls your including type 1. Type 1 error is the errors under the null,
it's equal.
right? And because we calculate under the null, we develop this such that the probability that this holds under the null, you don't want it to hold because this is rejection, but the probability that this holds under the null is exactly alpha. So we construct it so there's alpha. So if I like decrease alpha, this probability goes down. So I'm more likely not to reject under the null. So my type 1 error is going to go down, but then type 2 error is like missing, and I'm under the alternative is going to go up. So this significance level controls that the way you reject that the significance level means that not like 5% of the time, so alpha percent of the time, you allow yourself to make errors under the null. That's what it means. It doesn't mean that the actual thing is 0 or not, so you can't know it. But you know that if you repeat the experiment many times, 5% of the time you're going to be wrong. Okay. It doesn't tell you about that particular experiment, unfortunately. But that's what people like want to believe, that when we do reject this, there is actually something there. The statisticians, like if you really like understand what you're doing, you can't tell anything about that particular experiment that you're doing. You're saying, I'm doing this in the hope that if we repeat this many times, 5% of the time you're wrong. 95% of the time you're correct, hopefully. Like overall, around like, if everyone is doing correctly, only 5% of the results are going to be wrong. Not this particular experiment, we don't know. Sounds good. I'm going to try to come back to this point. It's like not that obvious, but that's what how statisticians obtain. You reject such that on average 5% of the time you're wrong, and hopefully you want this to be as close as possible to optimal. So that this is like very close. So I can try to like be like reject even when the value is higher. That would reduce it. So I could reduce my type 1 error, but then I'm gonna miss a lot of actual alternatives. So if beta 1, if I reject for very, very large values, the power, the like 1 minus type 2 error is called the power test is going to go down. So there's this balance. And so you'd reject at exactly the value that, so this is my tolerance. I'm going to exactly set it such that I allow like 5%. If you allow me to make errors 5%, I'm going to use that budget fully. So sounds good. So that's the t-test. So we tested one like beta 1 equals 0. Any questions? So hopefully you have seen this a lot, also probably in the section yesterday, but now you know how it's derived. Hopefully you understand what is going on and the significance of that result that we had. Now if I want to, let's do a bit more. I want to do, let's say, this was for h naught being beta equal to 0. I could also test, for example, h naught beta 1 is equal to, let's say, 2. If I want to do that. Doesn't have to be 0. Can I test for that? Yeah, you do beta 1 minus 2. The reason is like we know that in general, right, beta hat 1 is normal, which means beta 1 and sigma, like let's say v1 or v2, we said v2. That's like x transpose x inverse 2 to root. So if I have beta hat 1 minus beta 1, this is always going to be normal 0 sigma v2. So my like all the calculation that I did, like beta hat 1 minus beta 1, divided by the standard error of beta hat 1, this is in fact going to be t n minus d, no matter what. So under this holds always under the linear model. Assuming that the linear model is true and E2 is true, you can see that it's normal 0, and then if you go through the argument that we did, so this part divided by the standard error, this is the same as the standard error of beta hat 1. So if I subtract beta 1, the variance you can see doesn't change. So the standard error of this is going to be the same as standard error of beta hat 1. So if you want to really do this, you can do like beta hat minus beta 1, but the variance of standard errors, standard deviations, they don't care about the shift. So this is basically exactly the same argument goes through the T minus d. It doesn't have anything to do with the hypothesis. But now if I have like my hypothesis is that beta 1 is actually 2, so now beta 1 is 2 under the null. So plug in 3 here, you get that this standard error beta hat 1 is going to be under the null Tn minus d. Okay, so you can do like test other values easily. So this holds in general. Sounds great. So this is like beta hat, sorry, beta hat 1 minus 2. I can also build confidence intervals. So this result, so confidence intervals. So this result allows me to because this holds in general, allows me to compute like a confidence interval for beta 1. How do I compute the confidence interval for beta 1? So what is the confidence interval for beta 1? No, let's say step back. What is it actually? So forget about the null hypothesis. The confidence interval, like it's a separate concept, they're related, but let's say I want like a defined confidence interval. And I don't want to talk about like hypothesis testing. Can you just define it on its own? They're related, but maybe you can give it a try.
Percentage of confidence for example, if you're 95% of the time, without
Right. Okay. So it's good. So okay. So now maybe you tell me as well. You wanted to.
I'm gonna say that like 1 minus alpha percent under the true value of beta.
Yes, these are good. These are all good. I'm just going to make it a little bit more precise so that you can just, if someone asks you, like in the abstract confidence interval, like let's switch to the abstract version. The confidence interval in the abstract sense is just a random interval. It's like an estimator, but it's like an interval. It's a random interval that captures the true value of beta 1 and beta 1. I want to find the confidence interval beta I. So it's a random interval such that beta I belongs to this, or this contains beta I, it's probably 1 minus alpha. Okay, so this is like a precise definition. This is the abstract version. If you translate it to frequentist like interpretation of probability, it means that if I repeat the experiment many times, I get different realizations of this random interval. I had I, and if this is like saying beta indicator of beta I in this, so 1 is beta I in that interval 0 otherwise. So if I like take the average, like fraction of it, is the fraction of these realizations that capture beta I, that fraction approaches 1 minus alpha. Okay, so confidence interval is really the easiest way to think about it is a random interval. Beta hat is also a random quantity, is just a random point estimate. This is a random interval. Okay, so every time you do the experiment, you get a different interval. But like the probability that that random interval contains the true value that you're looking at should be 1 minus alpha. Sounds good. Okay, so this is the easiest way to define. And so now I have something like that. I can easily reveal the confidence interval. I want an interval. So we want I hat such that beta 1 belongs to this with probability 1 minus alpha. That's what I want to do. So how do I build this? So we want this. So I start from the one that I had. So beta hat 1 minus beta 1 divided by standard error of beta hat 1. I know that the probability that this is bigger than, let's say, the absolute value of t n minus d alpha over 2. This is very much similar to the test that we had. But this is not a test statistic, unfortunately. This is because it contains beta 1. I don't know beta 1, but this probability statement is true. So this is going to be 1 minus alpha. Because of the way that we discussed, this is in general true. Right? And if this is going to be under the regression model, we're going to have a key distribution. So the absolute value of it being bigger than this number, than some value, is going to be 1 minus alpha. And so this probability statement always holds. If you rearrange this, so this as an exercise, do for yourself. So exercise, rearrange. This is equivalent to saying beta 1 is in beta hat 1 minus this guy. I'm going to call this gamma. This is a number. Gamma times standard error of beta hat 1, and then beta hat 1 plus gamma standard error of beta hat 1. So this is just math. So this being an absolute value bigger than gamma means that either this is bigger than gamma or the negative of it is bigger than gamma. You write those two statements and you would just rearrange, take beta 1 out. So the same beta 1 is less than or equal to this, greater than or equal to that. Okay, so this statement is equivalent to this. You can try to manipulate it. And so this side you can see is a random interval. And we want it to be calculated based on data. So I know everything here. So I know beta, sorry, this is I hat. I know beta hat, I know the standard error of beta hat. This gamma is used from a table. I know n minus d, the alpha is what I said. So I know gamma. If it was normal, it would be like 1.96, but for that level that we usually use. But this is the confidence interval. So it's a random quantity. Every time I repeat the experiment, I get a different beta hat 1. A different standard error of beta hat 1, and so I get a different interval. But like if you do it like maybe 1,000 times the experiment, and look at all these intervals, and if I know the true beta 1, like hopefully 1 minus alpha of those intervals would contain. But that's sort of the confidence interval that we have. Okay. So this quantity, this sometimes called pivot. So this is called pivot. A pivot is a function of data and parameters, unknown parameters, such that its distribution does not depend on the unknown parameters. So it's not a test statistic or a statistic or an estimator. Estimators, statistics, these are things that only depend on the data, so you can calculate. Pivot is something that potentially depends on the unknown parameters as well. You can see this I can't in practice calculate because it can be bigger 1, but its distribution does not depend on the unknown parameters. The distribution I know, and these pivots are useful for building confidence intervals and doing hypothesis. So what we did, all the calculation that we did, independence, standard error, and beta hat 1 allows us to construct this interesting pivot. And this interesting pivot can be used to build confidence intervals, to do hypothesis testing, and so on. Okay. Sounds good. Questions? Let me do a quick example here. Back here. So example, I don't have the actual data, but this is an example from chapter 2. Simple linear regression, n is equal to 14, p is equal to 1. So there's one like hardness of spring or something. So there's one covariate and one intercept in the model. Beta hat 1 turns out to be negative 1.2. At this point, we don't know if it's big or not. But then you calculate the standard error is like 0.024. So compared to that, it's pretty big. But like if you have done things that you guess that this is significant. Okay. So beta hat 1 relative standard error. So you to make it more precise, you can build a confidence interval by like dividing, okay, not dividing. So if I wanted to do a test, I would do like test that beta 1 is equal to 0, what I would do is like beta hat 1 divided by standard error of beta hat 1, and compare it in absolute value to t with n minus d, which is like 14 minus 2. Alpha over 2 would be, or like, I would do this because that's positive, so 0.975. And so this would be like 2.18. So you divide that by the other one and compare it to 2.18, you can see like beta hat 1 divided by that quantity is much bigger than 2. So you'd reject. Or if you want to build a confidence interval, you like beta hat 1 plus minus this quantity times the standard error. You already know this. So this plus minus that. So that will be your confidence interval. So beta 1 belongs to this with confidence. So this doesn't mean that beta 1 is in this. So this is what I wrote is not quite reasonable. What it means is that this is one of those random realizations. Okay. I don't know if beta 1 is belong to this or not. You can't know. But if you do the experiment many times, you have a lot more of these intervals, and like 95% of those will capture beta 1. So this I don't like, but that's why they say contains with confidence 95%, basically saying nothing. So if you say beta 1 belongs to this with confidence 95%, it means that I didn't give you any information, except that if you repeat the procedure 95% of the time, that would happen. Okay. I just want to point out that you should understand that this is not useful. Confidence intervals are like, in a sense, not useful in a particular example. But it gives you some idea. You want to be like more like certain, but what really it does is like if you do many times, you can say something. Not for this particular example. Sounds good? Okay, so these, and I'm not going to spend time on the examples because I'm assuming that you know these. So what I want to do next is we can do more. I can even test any linear combination of the elements. So suppose I want to test 2 beta 0 minus 3 beta 1 plus beta 2 is equal to 0. I want to test something like that for some reason. Using the things that we develop, I can do that. How can I do that? The first step is to estimate. So let's say this is a new parameter. If you want to call it gamma views, like call it, what should we call this? Alpha, I like call it Kc. Okay, I have a new parameter Kc. We can repeat the experiment if I have an estimator of Kc, and if I manage to like make it like an estimate of the standard deviation of the Kc, and then replace it with standard error, and maybe things would follow. So the first step is to like find an estimator of this Kc. So what is that estimator? What is a good estimator of Kc?
It's a
2 minus
the dot term. 2 minus 3 plus 1 times beta hat is.
Oh, you want to write it like that? Okay, beta hat 0, beta hat 1. Okay, so you did the good thing. So I wanted to write it as like first, right? Like the plug-in estimator is good. 2 beta. I have an estimator of beta hat 0, beta hat 1, and beta hat 2. So just plug in. So this would be a good estimator. Good means that you can actually show that this is unbiased and you can actually calculate the variance. But this I can also write it as you pointed out, as this vector times. So this is the vectorial form. So this, let's call it A transpose, call this beta hat. So I can write it as A transpose beta hat. Where A transpose is this 1/3 vector. Right? So A I know, beta hat is, so we know that beta hat is normal, which means beta covariance sigma squared X transpose X inverse. The next step is to figure out the distribution, sometimes called sampling distribution. I have an estimator. Now I calculate the distribution of this. So what is the distribution of C hat? Sorry.
Normal.
A transpose beta, not beta hat.
Yeah, beta, yeah,
Yes.
and A transpose times you already know variance times A.
Okay, A transpose, I'm gonna write it as covariance of beta hat times A, which turns out to be sigma squared comes out, A transpose X inverse A. And because this is a matrix, this is a row vector, column vector, this whole thing would be a number. And you can see that Kc, this we call Kc. So you can see that Kc hat is unbiased for Kc. Its mean is Kc. And the variance is this. Now, if you look at this very closely, this is like beta hat 1 is normal beta 1 times sigma squared something. It's very similar to the form that we had for beta hat 1. So this new thing is gonna exactly follow the setting that we had. So sigma hat minus sigma. If I divide by standard deviation, it would be normal. If I divide by standard error, this would have a t-distribution. It's like the same idea. Standard error of sigma hat would be just, Kc hat would be just root of this. So standard deviation would be sigma root A transpose X inverse. Standard error would be just S root A transpose X inverse A. So because I have this, I can build a test. Building a test means like under the null Kc is 0, so it's just exactly similar. It's just based on this standard error. And I can also build the confidence interval. The only thing that changes is this value, the statistic and the standard error. In calculation, this part changes a little. But the rest goes through exactly as we had before. So the same idea is applied in this case. Okay, so I'm going to come back and try to finish these set of slides. So basically, let's say the midterm is all the way up to the end of these slides. So a few things are remaining, like this we already talked about, sort of for regression function. So like basically like 2 slides remains. Next time I'm going to come back and talk about that, but the midterm would be all the way up to these inference part 1. Sounds good? Okay. Thank you guys. See you next time.